Thanks for coming to the talk. Thanks for the introduction, Roberto. I'm talking to you today about combining physics-based and data-driven modeling for building energy systems, which was a project in collaboration with the EMPA Urban Energy Systems Lab in Dübendorf and the IMOS lab here at EPFL. So buildings are used every day for a variety of purposes, and there are several systems in place that actually enable building operations or enable their usage. For example, hot water, sanitary use, or cooking, lighting, electrical appliances, and so on. And if we look worldwide, the energy consumption that is used, around 30% of that total is actually used for buildings or building operations. And half of it is due to heating and cooling. So we see that there's a lot of potential to gain here. Especially in the light of global warming, we need to optimize the energy efficiency of the buildings. And in the light of digitalization, we can actually leverage the building information and the sensors that can be installed in the buildings to have a digital model of this building. And this digital model can then be used to predict the state of the buildings, for example, temperature or energy consumption, in order to then have a, let's say, decision making that enables us then to feed back the control loop. And this way we can optimize energy consumption and other, let's say, control systems in the building. And for this, we need an accurate and interpretable building energy model for this accurate, or let's say, robust decision making. The building energy model always starts with a physical twin, which has building information such as geometry, materials, and so on, but also sensor data for the surroundings, so weather data, temperature, relative humidity, and also inside the building, like occupancy, thermostats, and so on. And the end goal is having this building energy model. One way to go about it would be the so-called white box approach, where we organize the data first, structure it, and put it into a amenable form for the building energy simulator, and then we calibrate with real sensor data. On the other side, we have the data-driven or black box approach, where we engineer the features from the sensor data, then we select an appropriate data-driven model and train it. In the end, we have this digital twin of the building, the building energy model, and we can also co-simulate this with other systems surrounding the building, such as photovoltaic systems or electric vehicles and so on, and then predict the system's states. If we look at it from a physical point of view, then the white box approach is kind of solving a system of differential equations where we have detailed physical differential equations. One example for this is Energy Plus, that is widely used, which is a software from the US Department of Energy. And on the other side, the black box approach is more about input to output mapping with, for example, neural networks. And in the middle, we have a so-called gray box approach, where we use simplified differential equations, also called reduced order models. And then we actually identify the parameters through sensor data. And these three groups have different properties that we can analyze in terms of, for example, physical consistency. And because the white box models are based on system of differential equations, they have obviously very high physical consistency. On the other hand, black box or data-driven models do not have a physical constraint per se, so they are not physical consistent. Then in terms of modeling effort, we see that for the physical simulators, you usually need a lot of documentation to model the system correctly, which takes a lot of time. In our case, it was about half a year. And for the black box approach, usually it's quite fast, since you have a lot of data-driven libraries nowadays, like sklearn, which facilitate this process. And then when we go to predictive accuracy on new unseen data set, in the literature, the black box approaches or data-driven approaches, they usually perform quite well. For the white box approaches, since they are calibrated on a specific data set, it's harder for them to generalize to new data. And what has been done in recent years is trying to combine, say, these groups into a hybrid form. And one of these hybrid forms is the physics-informed machine learning. So they would leverage, say, gray box models in terms of simplified equations, and then put this into a neural network, for example, through soft constraints with a loss function. And one prominent example is the physics-informed neural network. On the other hand, people have also been combining, let's say, the white box and the black box as single systems. And such a combination is, for example, Energy Plus and a neural network, which we'll have a look at later on. And one example is the surrogate model. So when we train a data-driven model to replace the physical simulator. And as I just said, yeah, we will focus in this talk on the white and black box combinations. What we've seen in the literature is that the typical publications surrounding this topic, they always propose a new method. So and they show that their method is performing better. But what we were noticing is that there is no comprehensive comparison or overview. What are the advantages or disadvantages of such specific combinations of white and black box? So what we went on, we identified 4 groups of typical hybrid approaches, and then we compared them in terms of predictive performance, and had a look at disadvantages and advantages in case of a real-world example, which is at EMPA in Düsseldorf. The hybrid approaches that we identified in the context of our research were the assistant approach, residual learning approach, the surrogate approach, and augmentation approach. And starting with the assistant approach, we see that we have mainly 4 blocks here. One is documentation, the other one is the sensors, the Energy Plus or physical simulator, and the data-driven part. And in the assistant approach, we basically take the simulator output as an input directly to the data-driven part, besides the sensors. And then in this specific case, we had, for example, the temperature as a target, and the rest were the sensor data that were fed into the data-driven model. In the residual approach, the main idea is to learn with the data-driven model the difference between the real target, in this case the temperature, and the Energy Plus simulation. And then you would add this to the Energy Plus prediction, and then the sum of this would be your end prediction. Then the surrogate approach is maybe more common, where you learn with the data-driven model to replace the Energy Plus model, so you directly take the Energy Plus output as a target. Finally, the augmentation approach is kind of a step on top of the surrogate model, where we first learn on the output of the Energy Plus as a first step, and then as a second step, we fine-tune, or we take the real data as a kind of fine-tuning data. So now we had, let's say, all these approaches, and we went to our building at EMPA, which has this big demonstrator with a lot of units that are used for a variety of purposes, which are either residential or commercial. So people live there, people work there. There are also different, I think there's a gym, a sauna, so you can visit if you're interested in, and there are different research projects going on. And we also equip all the units with a lot of sensors. There's one specific unit that is the interest of this presentation, which is the urban mining and recycling unit, where a lot of new materials are tested. For recycling purposes and insulation measurements and so on. And we have 5 rooms that we model here, 2 bedrooms on the left and right side, the living room in the middle, and then 2 bathrooms in the back. And this unit is actually rented. by usually researchers for let's say a lower price, but they forfeit the data privacy. The sensors that we install outside are, for example, weather, so temperature, radiation, humidity, and wind speed on top of this nest. And then we have building like mass flow sensors, network temperature sensors, air conditioning sensors, and so on. And on the room level, we also have like set points, occupancy, window, opening measurements, and blind position measurements. For this specific case study, we took 1 year of training, 1 year of testing, 50 minutes of resolution. We did room temperature, let's say regression, and we optimized the mean squared error. Just to remind you, we tested all 4 of these hybrid approaches. The white box part would be an energy plus model, and the black box part, we used several algorithms to have a comparison. So linear regression with abbreviation LR, the feed-forward neural network, and the random forest. So on to the results of the room performances in terms of MAPE. And here you see the Energy Plus simulator, which is EP, and then the data-driven part, and then the other hybrids for the different combinations with linear regression, feed-forward neural network, and random forest. And one of the things that you could ask is, how does the simulator as a benchmark perform? And we see that actually most of the hybrid approaches have a better predictive performance in terms of MAPE as the Energy Plus model directly. The worst performing was here the surrogate model. One of the reasons was that, I mean, it's for one limited by the Energy Plus model because it tries to replace the simulator. So it's kind of an upper bound. And also the assumptions of the white box model, let's say regarding the occupancy, were not ideal. So the surrogate model was also confused with that. The other thing is that, okay, the other hybrid approaches perform better. And if you look at it, let's say on average, they performed quite similarly with a very slight advantage here for the residual feed-forward neural network. The other thing that we could notice is that there's actually a variance between the best performing models for room types. So for example, bedroom or bathroom. And what we can see is that actually the residual has, let's say, 3 of these rooms that are best performing, and which indicates that room type could also be something that could be differentiated, maybe with different models. So as a small conclusion, the residual approach has the best performance, and there is some variation across the rooms for the best models. One reason for for this performance of the residual approach is here this plot, which shows the temperature over, let's say, the month of March for all the methods exactly. And so the blue one is the real temperature, which we see, bird. And there's a steep drop, as you see, around 6th of March and 13th of March, where the residents actually left the window open, which in the test set was a very singular or out of distribution event. And luckily for us, this was an interesting case to look at. And here we see that when the temperature drops, for several days, then the physical simulator in red will also capture this behavior. And because of that, the residual feed-forward neural network, because we're taking here the feed-forward neural network as an example, representative also for the other methods, is also able to identify that, because it's in the end, it takes the basis as the simulator and then adds or subtracts a delta. And for the other methods, be it the neural network only, let's say as a black box model, or the other hybrid combinations, they are not able to detect that steep drop. So they have a prediction more closer to the temperature mean. Exactly, and here again, the residual has the most physically plausible out of the hybrid approaches. Then we went on for the data quantity dependency. So what happens if we reduce the training data, but still test on the test data, right? And here on the left, you have the 12-month, which we just had a look at, 12-month performance, and then we gradually decrease the training data. And what we see here is actually that the trend is upwards, which makes sense. So the error increases in terms of MAPE if we have less training data, with two exceptions. One exception was here for 3 months, where we had an issue with the validation set. So validation set had a special structure, which complicated the conversions of the neural network. And for the first, or for 1 month, there was also, let's say, an evaluation artifact because the predictions were closer to the mean. But maybe to show you how this looks like for 1 month, also to show you this distinct behavior. So for the feed-forward neural network, you see that it's not learning quite the variance of the temperature on the upper side, because of the only 1 month of training data. In comparison, the residual feed-forward neural network, which leverages the simulator, is better at capturing, let's say, the full variance of the temperature. Here again, yeah, the residual approach is the most robust. Then we also went on. So here, this is actually the same slide as before for the room performances. But what you could ask yourself is, okay, this is an Energy Plus model. We had almost half a year to set it up. So it's the modeling detail is high, but also the complexity to set it up is also very high. And the other thing is that the nest building has a lot of sensors, which is more of a research setup. But what happens if we have less sensor coverage? And if we condense this plot into, let's say, a box plot, which is the same, just in a different form, with detailed modeling, all sensor inputs, let's call it, so weather, building, and room level sensors. Then we compared it to a simplified model, which was done with a, let's say, framework from the Urban Energy Systems Lab, which is called CSRP, and only inputting the weather. Then we see actually that performance is already quite high. So the MAPE, if you see here at the 4% line, we are maybe at 4.3, 4.5, only with the simplified modeling and the weather input. So this already provides a quite good basis. And then if you want to go below for MAPE, then we can achieve this by higher modeling and more sensor inputs. Exactly, this is the kind of the conclusion that these hybrid models can also, let's say, fill up the performance also with simpler models. Yes. In summary, we had this deterministic framework with the hybrid approaches, with documentation sensors, the simulator, the data-driven part, and the point prediction. But from an operational perspective, you can always ask yourself, okay, is this future really that certain? Or there are, let's say, uncertainty factors, right? Where exactly does the prediction go? And two sources of uncertainty, at least in the building energy modeling framework, are weather uncertainty, but also operational, let's say, occupancy uncertainty, because the behavior changes of the tenants or the residents. And this calls, let's say, for a probabilistic view of this framework, which was our extension. And here, the probabilistic part was the data-driven part that we exchanged with a probabilistic model. And then in the end, we chose a quantile framework to produce, say, the quantiles of the distribution for each time step. And in our case, these were 99 quantiles. So just to give a quick summary, we again used the hybrid approaches. For the data-driven part, we used the so-called quantile loss, which was optimized with all the models. So for the linear regression, we would then get a quantile linear regression. For the feed-forward neural network, a quantile feed-forward neural network, and then for the random forest, a quantile random forest. And then we would produce for all the models these 99 quantiles. And also, if you choose two quantiles, let's say upper quantile and the lower quantile symmetrically to the median, you would get a prediction interval, and then you could have, let's say, uncertainty prediction intervals. And Just to give you an example, how this would look like. So for the 90% prediction interval, this is the plot again for this special period in March that we showed for the windows with the window openings here. And the situation is similar since the residual quantile neural network is the only one able to detect this drop with the uncertainty, with the 90% prediction intervals. And the other ones, assistant, augmentation, and so on, they still have this, let's say, mean view or median view, and they are staying on the upper side of the predictions. So here again, we can also say that the residual quantile neural network has the most physically plausible predictions. And we also see that the energy plus here in gray, in the gray dotted line, it's kind of the basis, and then the quantile neural network puts on the prediction interval asymmetrically, which is also an advantage here. Then as a small outlook, what we could improve for the specific case of the residual quantile neural network in the case of the bedroom is, if you see here all 99 quantiles, let's say from yellow, from the upper ones to the lower ones, which are in violet. And one of the things that is, I would say, positive about that specific method is that when you have a temperature drop here in black, then the distribution becomes asymmetric. So the lower part is higher, if you see that here, which makes sense, because if the temperature drops, then it's more likely that it will drop more in this case. So for us, this makes sense that it has kind of an asymmetric part. In the other case, where the temperature rises sharply, we see that there's a distribution collapse here. So actually, all the quantiles kind of go through very narrow point, and we think that that would be a point to start improving this model. Exactly. So the dynamics, the fast dynamics, there's still some work to do. In conclusion, we saw that of all these hybrid approaches, the residual approach is the most effective overall, in terms of performance, but also in physical plausibility. We also saw that performance varied across room types. So yes, so for example, maybe we would need to treat the bathrooms different than bedrooms, because also the thermal dynamics are very distinct. And that out of distribution events are very challenging in such situations, especially if they're not present abundantly in the training set. As an outlook, we already have a project ongoing that tries to embed these hybrid approaches into a control loop for, in our case, it would be for reinforcement learning. And then we would also test it in this facility, because we have all the infrastructure to test out the control algorithms. Then there's also a project that we could scale up this methodology, because this was a very particular case, a research building. But what happens if we scale this up for 100 residential buildings, for example? So we would need to do a statistical analysis if this really holds. And finally, the online deployment would also be interesting to see what happens if these models need to be updated. So would we still stick to, let's say, this batch view or offline view, or would we switch to online learning cases? Exactly. If you want to know more about the things that I talked about, these are the two publications that we have. And that's all. Thanks for your attention.